Okay.
From which university the second so Martin González?
He's Cándido Martín González, and he's from the University of
González.
Málaga in Spain.
Martin
Málaga.
Yeah, from Málaga. Okay.
Yes.
Is he student of
No, he's well, I think he's in his 50s or 60s probably.
Oh.
I don't know. I think he's a full professor in Málaga. He has been working recently in evolution algebras and Levy-path algebras, and also some years ago, I think he worked a lot on Jordan algebras. And Ivan, as you all know, I guess, he was one of my PhD advisors.
Okay. So let's start our seminar. Pilar, please.
Okay. Well, thank you very much for the invitation and for the for the presentation. Yes, I'm going to speak about this joint work with Ivan from the University of Beira Interior in Portugal and Cándido Martín González from the University of Málaga in Spain. And the topic of the talk will be central extensions of axial algebras. So the first thing we have to do, or at least the first thing we are going to do, is to define what is an axial algebra and to understand them. So these algebras are a quite recent type of algebra. I'm not going to say variety. Introduced in 2015 by Hall, Rehen, and Spektorov. And the definition, well, do you hear me correctly, right? Yeah, okay.
Yes, yes.
Okay, thanks. So what are axial algebras? They are going to be commutative algebras, which are generated by idempotents. These idempotents have to verify some conditions. They have to be at semi-simple. So the operator multiplying by the left has to be semi-simple or diagonalizable in finite dimension. And the associated eigenvector decomposition has to satisfy a certain fusion law, whatever that means for now. So as the definition is not the easiest thing ever, let's say it that way, I thought it would be nice to begin with some examples. Let's take a Jordan algebra, a commutative algebra in which the elements satisfy also the Jordan identity. Okay, this is known as interesting feature of Jordan algebras is the so-called pairs decomposition. Whenever we have an idempotent, then the operator multiplied by the left, or in this case by the right, as the mother, by my idempotent A, this operator has always three eigenvalues, 1, 0, and 1 over 2. Well, we need to ask, of course, the characteristic of the field to be different from 2. And this operator is semi-simple, diagonalizes, and we can decompose our algebra in the direct sum of the eigenspaces. Okay, I am going to denote always the eigenspaces in this way. As a subscript, I'm going to have the eigenvalue, and as a superscript, I'm going to have the idempotent A associated to the decomposition. Okay. So what happens with this decomposition? Well, that when we multiply elements from these eigenspacings one with another, there is a fixed rule that this multiplication, this product, obeys. I have written here it explicitly, how are the products of these components, but we can also take a look at these rules in a compact way with this kind of squares of tables telling us yes how to multiply. If I take elements from the subspace, from the eigenspace associated to 1 and multiply them with other elements in the same eigenspace, I still get a new element in the same eigenspace. And for example, if well, when I don't write nothing here, this means that the product is always 0. In this case, whenever I multiply from eigenspace 1 with eigenspace 0, the result is always 0. And well, on 1/2 times 1/2, I get an element which is in the direct sum of the eigenspace associated to 0 and the eigenspace associated to 1, as is written here. Okay, so we have rules of how to multiply these eigenspaces. Another example, which was very important, is the Gris algebra. It's a commutative algebra, a real commutative algebra of dimension, well, huge dimension, which is was very important when it was first devised, as the first time that this group, the largest sporadic simple group, the monster, was constructed. It was constructed by Gris as the automorphism group of this Gris-Norton algebra. Okay, and what happens with this algebra? Well, something similar to what happened with Jordan algebra. It is generated by idempotents. These idempotents, well, the operator, left multiplication, but them have always 1/4 and 1/32, and is semi-simple, so we can decompose our algebra. Okay, we can compose our algebra, the direct sum again of the eigenspaces, and we have again some rules how to tell us how to multiply these. Yes, and also let me point out that this Gris algebra can be found as the weight 2 component of a vertex operator algebra, the moonshine vertex operator algebra, related to Borchers, I don't know very well how to say it, moonshine conjecture and proof. So, as the vertex operator algebras are such complicated objects, people studying them decided to also focus a little bit for some purposes on their weight 2 components. So they defined the generalized Gris-Norton algebras as these weight 2 components of VOAs. And after that, these components were the object of new generalizations. The first one, I think, were the Majorana algebras introduced by Ivanov, if I recall correctly. And another generalization is going to be the axial algebras, our object of study. The good thing about the axial algebras is that they also are going to recover Jordan algebras, for example. So we have a common frame to study these generalized Gris algebras, these Majorana algebras, and Jordan algebras, and also other algebras related to physics. Well, so now that we have these examples in mind, let me go back to the definition of an axial algebra, and let me introduce it properly and correctly. So, a certain fusion law. What do you mean? What do I mean with this? Well, let's take our ground field and let's take a subset F of our ground field. So the fusion law is going to be just a mapping from Ames times F times F, sorry, to parts of F, which has to be symmetric. Okay. If we want to have an example in mind, we just pick the tables that we had before for Jordan algebras and for the Gris-Norton algebras. And well, here what we are saying is that in this case, for example, for the Jordan algebra, my set F is going to be 1, 0, and 1/2. And my product star, my bilinear mapping, my symmetric mapping star, is just going to tell me that 1 star 1 is 1, 1 star 0 would be the empty set. But we just, by convention, don't write anything. And I don't know, 1/2 or 1/2 star 1/2 is going to be the subset 1, 0. But again, we don't write the brackets. Okay, so these are two typical fusion laws, which can be generalized to the fusion laws that we call of Jordan type. Jordan type, in which is the same as the one that I presented for Jordan algebras, but instead of having 1/2, I have a parameter theta, and also the monster type with 2 parameters, alpha and beta, which generalize the fusion laws of the Gris-Norton algebra. Okay, so these are the fusion laws. Let's go back to the axial algebras. Commutative algebra generated by these idempotents, which we are going to call axes. So an axis has to be an idempotent for sure. The left operator, the left multiplication operator has to be semi-simple, so we can decompose A into a direct sum of my eigenspaces, where I am using the same notation as before, the eigenspace as a subscript and the eigenvalue as a subscript and the associated idempotent as a superscript. Okay, and how do I relate this with the fusion law? Well, the spectrum of the operator has to be contained in my subset F, and the mapping star is going to tell us how to multiply the eigenspaces, the same as we saw before in the example. So I am eigenspace associated to lambda times eigenspace associated to mu has to be contained in the eigenspace associated to lambda star mu. Okay, so these are the axes associated to this fusion law star. And an axial algebra, well, I need to fix a set of generating axes x, and my axial algebra is going to be the... Sorry, can you repeat? Sorry?
Who is talking? Who is speaking?
Sorry?
Go on, go on.
Oh, okay. It was perfect. I thought it was a question, but I couldn't understand it. Okay. Nice. So yes, I was saying that we need to have, apart from the algebra, we need to fix the set of generating axes. So the structure constructed in this way is going to be called axial algebra with respect to the fusion law that we also fixed. Okay, so these are the object of study. Let me, and yes, a couple of examples are the examples that we saw before. Not all Jordan algebras are generated by idempotents, but the ones who are for sure axial algebras with respect to the fusion law of Jordan type 1/2, and the Gris algebra is also axial with respect to the fusion law that we saw before of monster type, where the parameters are 1/4 and 1/32. Okay, so yes, I'm going to speak a little bit about a couple of properties, because one of them will be kind of necessary for later, and the other I think is interesting and is one of the main aspects of axial algebras. So primitivity. We say that an axis is primitive when the eigenspace associated to 1 is just the linear span of my eigenvalue, of my idempotent. Sorry. And if in my set X of fixed axes, all these generating axes are primitive, we say that the axial algebra is primitive. So there are many authors that just only consider primitive axial algebras, because all the motivating examples or the interesting examples are primitive. So at some point they just decided to drop this condition primitive and assume that it's part of the definition. But in our work we didn't assume this, so we distinguish between the primitive algebras and the non-primitive algebras. Okay, yes, and I wanted also to speak about the Miyamoto group with respect to a set of axes y. Well, this Miyamoto group, well, this is going to give us a connection between the algebra theory and the group theory, one more. And okay, we can only compute these Miyamoto groups whenever the fusion law has a grading. And again, most authors just restrict themselves to work with gradings on set 2. So what do I mean with a grading of a fusion law? Well, I'm going to assume all the time set 2. So what do I mean with a set 2 grading in a fusion law? Just a partition of F into 2 components, 0 and 1, such that whenever I do the star product of the 2 components, well, the result is contained in the component, in this case, I plus j, as I am using the additive notation. So whenever I have a fusion law which is graded, this grading induces another set 2 grading in the algebra. I just need to put together all the eigenspaces associated to eigenvalues in the 0 part. This will be the positive part of my algebra. And also I need to put the eigenvalues associated to the 1 part together, and I get the negative part of my algebra. And recall that this grading depends always on the axis A that I'm considering, okay, on an axis A. Okay. So let's fix a set of axes Y, which has is not necessarily has to be the X set of axes of the. So my Axial algebra is AX, but I'm going to consider another set of axes Y, which can be the same as X or can be different. And where to define for any of these axes in Y, we are going to define an homomorphism between set 2 and the group of automorphisms of A. The 0 is going to go to the identity of A, and the 1 is an automorphism defined in the same way. The X, the elements in the positive part of my algebra remain invariant, and the X's in the negative part, we just change the sign. Okay, well, and then of course we extend this linearly. Well, then if I consider all the images of all these tau sub A element homomorphisms for all the axes in this set I, and I consider the subgroup that this generate inside the automorphisms of A, this is what we call the Miyamoto group of A with respect to Y. And well, why is this interesting? For example, if we go back to the Gris algebra, and as I told you before, that the monster, this largest sporadic simple group, was the automorphism group of this Gris algebra. But we can also see it as the Miyamoto group with respect to a set of axes. We need to select some kind of axis in the algebra, and we can do it in that way that we only need 3 axes. So we have a very nice description or a very nice presentation of this monster algebra. Okay, so now we have the algebras, and as whenever we find an interesting object, we would like to classify it, to classify the different objects and the different algebras. So that's what people began to do. When I say people, I'm talking about Hall, Spektorov, Rehren, McInroy, Mainardis, Frankie. There are a lot of people working on this. Okay, so the classification. The classification has followed 2 main directions. On the one hand, there is the classification of algebras of monster type. This is not complete, but I do not want to delve into this as we haven't done anything in this direction. I'm going to focus on the algebras of Jordan type. So when the parameter eta is not 1/2, the classification is known, and this is thanks to we can associate the algebra to 3 transposition groups, which are also classified. So the classification comes from the classification of 3 transposition groups. But the problem comes when we have eta equal to 1/2. So in this case, we found the Jordan algebras generated by the idempotents. We found these Matsuo algebras, which are again related to 3 transposition groups. And it is an open question if there are more or not. For example, for when the algebras are 2 or 3 generated, it is known that there are no more algebras. No more axial algebras of Jordan type 1/2, apart from Jordan algebras and quotients of Matsuo algebras. But in the general case, this doesn't have to be the case. And how can we contribute to this, or at least how can I contribute to this? We thought about working on central extensions of axial algebras and trying to get new algebras, or well, try to throw a little bit more light into this subject. So I'm going to speak, to spend, I think, the next minutes speaking a little bit about how to use the central extensions as classifying tools. So very briefly, let me recall that by a central extension, I mean a short exact sequence such that the image of V is contained in the annihilator of V, the algebra in the middle. So I call this at least a central extension of A by V, and I'm going to say that the dimension of the extension is going to be the dimension of here V. So the dimension of this one minus the dimension of this. Okay, so this is the general expression, but we can particularize a little bit the situation. So instead of the algebra B that I have here, I'm going to write this A sub theta, which is defined in the following way. As the underlying vector space is going to be the direct sum of A and B, of course, and we are going to endow this vector space with the following product. So if I do this, well, with the following bracket, let's say, if I do the bracket of x plus V and y plus W, well, this is going to be defined as the product of x and y plus theta of x comma y, where theta is going to be a bilinear map from A times A to V. Okay. And the interesting thing here is that if you check in the definition before, you can see immediately that this is a central extension, but also every central extension can be seen as some A theta for a certain theta. So this is what is going to be our idea of central extensions. Okay, what else? Yes. And I said that I wanted to speak about central extensions as classifying tools. So this A sub theta are going to be the key part, let's say, of the method of Skelbrand Sand for classifying nilpotent. Well, in the first time classifying nilpotent Lie algebras, but then we can forget about Lie and write adaptations of this method for every variety of algebra defined by polynomial identities. More or less how this works. Well, I take my variety M and I can construct a central extension, A theta, but I'm going to be interested in that A theta is going to be again an algebra in the variety M, in the same variety as the original algebra. And we are going to find that this is equivalent to theta satisfying, well, certain related identities. For example, if I pick the variety of Lie algebras, of course defined by the anticommutativity and the Jacobi identity, I have that my central extension A sub theta is again Lie if theta is antisymmetric and satisfies this kind of modified Jacobi identity. And also, if we want to approach this from the point of view of cohomology, this is the same as saying that theta is a two-cocycle with respect in the Eilenberg-Chevalier complex with trivial coefficients. If I take another variety, I'm going to choose now commutative because it's going to be nice for me in my axial algebra setting. So commutative algebras, the only polynomial identity involved here is a commutativity. So I'm going to have a unique condition on theta, that theta is symmetric, for obtaining that the extension a sub theta is again commutative. Or also, from the cohomology point of view, theta is a two-cocycle in the corresponding cohomology again with trivial coefficients. Good. So we can completely characterize when a sub theta is in the same variety in terms of the identities satisfied by theta. And well, in this case, we say that theta is going to be a two-cocycle with respect to this variety. Good. Yes, and the main point on this is not that we can construct a central extension. Oh, okay, we construct new algebra. Yes, that's very nice, but the most interesting thing is that whenever I have an algebra B in my variety with non-zero annihilator, then B is going to be isomorphic to a central extension of another algebra A with small dimension. Here it is in the same variety where theta is going to be a two-cocycle. So this is going to be super useful for classifying the algebras, at least with non-zero annihilator, and this is why the nilpotent algebras are often classified by this method. But of course, okay, we can construct extensions. We know that every algebra is going to be an extension, but we need to solve the isomorphism problem. And we want to solve it in terms of the two-cocycle theta. So the first thing to do clearly is that the isomorphism class is not going to depend on the cocycle theta, but on the class of cohomology. So we have our two coboundaries, which we denote by B2, as usual, given, okay, by this type of cocycles, which come from a linear map F. It's written here, sorry. A linear map F from A to the vector space V. Okay, we can define, given this F, we can define my two coboundary as a bilinear map with this definition. So, yeah, we quotient, we get the cohomology, and the isomorphism class of my algebra is going to depend on the cohomologic class and not on the cocycle. Also, we have that the automorphism group of the algebra is going to act, well, it acts on the cocycles, and the action is inherited in the cohomology. So we have the next result that tells us that the algebras which are associated to the cohomological classes in the same orbit are going to be isomorphic. And with this, roughly speaking, we solve the problem, except that we can have some kind of technical problems with the dimension of the extensions. We can like construct an algebra as a one-dimensional extension of another algebra, and also as a two-dimensional extension of another one of a smaller dimension. So to avoid these problems, we impose technical conditions on the annihilators of the algebras, and everything goes well. And as I said, this method was developed for all the algebras, for classifying nilpotent algebras, but it can be adapted to any variety of algebras defined by polynomial identities. But, oh, sorry, I was forgetting this part. Yes. We are not going to be interested in all central extensions, because, for example, if I have just an algebra and I do the direct sum with a copy of the field, this is going to be an extension, but this really doesn't give us more information than what A did. So this is a split central extension, but we are going to be interested in non-split central extensions, which can be defined in the following way. is going to be non-split if we cannot decompose it into the direct sum of an ideal I and another ideal, which has to be contained in the annihilator of A theta. Okay, we cannot decompose it in the direct sum of two ideals, one of them in the annihilator. And these are the algebras which we are going to be interested. The central extensions in which we are going to be interested. Okay. So, as I was saying, this is works perfectly whenever I have a variety of algebras defined by polynomial identity. Sorry, but okay, sorry. Yes, as I was saying, with my Axial algebras, I cannot apply this method in principle because they are not defined by polynomial identities. But we wonder, okay, what can we recover? Is it possible that this method still gives us some information? And well, the very first thing to start with is that the axial algebras are commutative. So if I have an axial algebra and I want to construct a central extension and say, okay, when is this an axial algebra? I know that it has to be commutative. So I know that my theta is going to have to be symmetric. So, okay, we can, that part is already solved. And I can ask myself the following. If I have a commutative non-split central extension, what are the conditions on theta which ensure me that a theta is going to be axial again for a certain set of axes and, well, for a certain fusion law. Here I wrote the same fusion law as the one in the original algebra, which would be the most desirable situation, but also we can construct axial algebras in a different with a different fusion law. Okay, so let's solve the problem. Yes. Okay, this is written more or less the same. So I wonder when is a theta and some set with some set of generating idempotents I, when is it axial? Well, where do we begin by looking at this set I? We already had idempotents in the original algebra. In the original algebra A, I have this set of generating idempotents X. So let's see what happens with them. I take one of these elements in A, and I'm going to apply the new product in the extension A theta. So it was defined as in the first component, we have just the old product of A's, and then I have this theta of AA. So this is for sure A, as it was an idempotent, and I have this new term, theta AA, which is bothering me, let's say. But the interesting thing here is that if we take this original set of axes, X, linearly independent, we can assume that this theta of AA is going to be 0 for all these A's in X. We just have to consider a different representative of the cocycle theta. We define ad hoc F. We can change the representative and we can assume that this is 0. So I'm going to take a new hypothesis by now. I'm going to consider just minimal set of axes generating the original algebra. Minimal in the sense that no, well, of course, that no smaller set is going to generate the algebra. And of course, in this case, if X is minimal, it's going to be linearly independent, and I can assume that this is 0, and then I have that the product within the bracket in the new algebra gives me again A. So the elements in X are going to be idempotents also in the new setting. Okay, so I want to change my question, and instead of saying let's find a a set Y such that a theta comma Y is axial. I'm just going to work with a theta comma X. Okay, so now we know that these are idempotents, but in the definition of axial algebras, we ask these idempotents to generate the whole algebra. And this indeed is going to be the case. This is some technical proof, which tells us that the algebra generated by X in the new setting theta is going to be the whole A theta. And for this, we need explicitly that my extension is non-split. Okay. Well, so now we have a set of idempotents which generate my A sub theta, and we will go to the the main properties of the axial algebras, which tell us that the multiplication, the operator multiplication by the left has to be diagonalizable. And we have this even if the kernel of this operator is contained in the radical of theta with respect to A. Okay, and this more or less solves the problem. When all these conditions, commutative non-split centralization, X minimal, and this kernel contained here, we have that A theta X is axial. And okay, yes, because we have this semi-simple, etc., etc. So the last part of the definition is that the decomposition of the algebra in the eigenspaces has to satisfy, when you multiply it, has to satisfy a certain fusion law. But in this point, I could take my decomposition, see how it works, and define my fusion law ad hoc. Okay, that could be an option for sure. But let's take a look at what happens really here, and let's also think, okay, and when can I have my original fusion law? Because maybe I'm interested in preserving the fusion law. So the fusion law that we obtain always is going to be this one. The set of eigenvalues is going to be the same as before, and maybe we have to add the zero. I mean, the zero has to be in this setting of the central extension, but of course, maybe it was already there. So f and 0 and a new symmetric map, but a new symmetric map very similar to the previous one. Or I have that is the same as the previous one star, or it's going to be the same plus the 0. Okay. Well, as I said before, sometimes we're interested in having exactly the same fusion law. And we can characterize this, and we did characterize this, but the condition is quite horrible and technical, so I decided not to write it here, just say that this can be perfectly characterized. And when these conditions hold, we are going to say that theta is a two-cocycle in our setting, okay, with respect to A, to V, and to the set of generating axis X. So, long story short, this is well written, what I was telling before. Well, you can read it again, but there is nothing new there. Just the conditions, and saying that the fusion law is equal if and only if theta is a two-cocycle. This is these technical conditions and horrible conditions that I said before. Okay, so this characterization can be generalized to the case when X is not minimal in a not difficult way, and it's just more technical and it's more difficult to make the computations, but it's not theoretically, it's not more involved. And also the method, we thought that it was interesting as it allows us to relate properties of the original algebra A, which has smaller dimensions. So these properties are easier to compute as, okay, is the algebra primitive? What is the Miyamoto group of the algebra? And other properties that I didn't introduce, but well, that, of course, they are smaller and they are easier to compute in a smaller algebra. So we can relate them with the properties of A theta. In many cases, the properties of A and some easy condition on theta tells us immediately the properties of A theta. But the main point and the real importance of this is that, as we had as I told you before, for the algebras or for any variety defined by polynomial identities, for axial algebras, we also have the following situation. Whenever the axial algebra has a non-zero annihilator, then it is going to be isomorphic to a central extension for some other axial algebra A and some cocycle theta. Okay. And what other things that we can do with this? All these things about the state of the classification that I told you before, we thought, how can we use this for trying to help, let's say, in this problem? Well, now that we have this situation here, that every axial algebra with non-zero annihilator is a central extension, it made sense to say, okay, let's look in central extensions of smaller algebras to see if we can find new axial algebras, or we can cast some light on this problem of the Jordan algebras, well, axial algebras of Jordan type 1/2. Yes, okay, I should have spoken with this slide. Yes, okay, so in particular, we are going to focus on this. Can we find more Jordan algebras of type 1/2? In particular, if I pick a Jordan algebra which is axial, so which is generated by idempotents, and I compute the central extensions, what I am going to find? Well, I compute, central extensions with respect always to the fusion law Jordan 1/2, which are the one in which we are interested. What are we going to find? Are we going to find Jordan? Are we going to find Matsuo? Doesn't seem very likely, but or can we find something new? Well, so we decided to study first simple Jordan algebras over C, okay, of finite dimension. We took the classification and studied the central extensions with respect. Of course, I need to fix my set of idempotents with respect to the set of all idempotents. Well, we found that there are no non-split axial algebras of Jordan type 1/2. Axial central extensions of Jordan type 1/2. And this is also interesting because this generalizes the situation for Jordan algebras, because we have the same. If we compute the central extensions, but as Jordan algebras, not as axial algebras, of course, we find that there are no non-split central extensions. Okay, so if we broaden a little bit our perspective, and instead of working in the setting of Jordan, we work in the set of axial, again, the same situation, no non-split extensions. Okay, so here we don't find anything else to add in our question. Then we also consider three families of Jordan algebras. The first one only with a semi-simple part, just the direct sum of the idempotents. And here we found that, again, there are no non-split axial central extensions. And for these two other families, this is supposed to be Gn and this is supposed to be Tn. We found that whenever we have a central extension of an axial central extension of type 1/2, this is Jordan. So again, no more algebras here. Yes, and I want to point out that in the previous case, we only work with the set of idempotents, okay, the set of all idempotents. Results are independent on the set of axes. You can take whenever, and the result is always the same. Okay, and using these families and some other easy tricks to select things and so on, we consider the classification of all Jordan algebras or all Jordan algebras of dimension less or equal than 4 over an algebraically closed field, and we prove that every non-split axial central extension axial of type 1/2 is going to be Jordan. And again, this was for the practice that we want to consider. So we dare to make a conjecture that if we have a field, of course, in all this setting, we need to ask the characteristic not to be 2. If we have a field of characteristic not 2, we conjecture that every axial central extension of type 1/2 of Jordan algebras which are axial, so of Jordan algebras generated by idempotents, is going to be again a Jordan algebra, and probably with respect of any set of such generating idempotents. And I do not dare to conjecture if there are more algebras or not, more axial algebras of type 1/2 or not. I'm not so expert by far, but it seems that with central extensions, this is going to be the case, that whenever we start with Jordan, we are going to end in Jordan. And well, as I think, yes, this is it. This is the base, as I said before, in this work with Ivan and Candido, which I hope that we can submit it in the next few days. And that's everything. Thank you very much for listening.
Thank you. So any questions or comments? I have a question. So if the Jordan algebras, yes, you consider
Yes.
it has 3 axes, yes? 0, 1, and 1/2.
Yeah.
But are they the unique algebras, axial algebras with such axes, or maybe not Jordan algebras also?
Okay. No, of course there are more axial algebras with this set of eigenvalues. You just change your fusion law, and you get a new type of axial algebras. But people are interested in that precise fusion law because it's the one of the Peirce decomposition. So that's the one who appears naturally. But you could have other axial algebras with these 1, 0, and 1/2 eigenvalues.
And are they necessary commutative or not necessary?
The original definition was with commutative algebras, but there are new generalizations working with non-commutative axial algebras. I think Rowen and Segev are working with them, and they had 2 or 3 papers. One of them is very recent, working with this.
Okay.
Yeah.
More questions?
Assalamu alaikum. Hi, Pilar. I have one question.
Hi.
Okay. So, is it somehow related to vertex operator algebras, these axial algebras? Is there any connection?
Yes, the axial algebras are supposed to be a generalization of Majorana algebras, which are supposed to be a generalization of the 2 component in the vertex operator algebra. So, well, I read things about these vertex operator algebras, but as I don't know a lot, of course. But I recall that they have this grading, and in the second component is when you can find, for example, the Gris algebra or other generalized Gris algebras, and these are supposed to generalize these two components.
I see. Okay, thank you.
May I ask a question, please?
Yes.
Sure.
In fact, the central extension for more simple classes of algebras, say for Lie algebras, for associative algebras, and some other simple classes algebras are very computational. But in your case, your algebra, your class of algebras is the definition itself is difficult. It is not like say Lee and the other classes of algebras, but so in your case, that computations will be super computational, because some of results for Lie algebras case say that correspondence between action of automorphism groups on subspaces of cohomology group and isomorphism classes. This correspondence you should do reproduce again, because for each class of algebras that result is proven separately, because it depends on class of your algebras. But in your case, it should be reproduced again. So that's why I think that you will face some difficulties, not only in computational problem, but you will get some problems proving some simple application of simple central extension to your algebras, I guess, because your algebra class of algebras, as my feeling, you're just taking some particular cases for your algebras and they start to classify them. It is not a complete classification, of course. So you will get some problems.
Yes.
So how to be this case?
It's yes, you are totally right. That is more complicated than if you have an easier definition of the class of algebras. So, but it's if you are working with small dimensions, for example, from the computational point of view, it's not that complicated, as you can write the conditions that I have. Let me see.
But general theory you should reproduce, because you're just making some theory here for your class of algebras. So that's why that theory for Lie case, for associative case, or for Jordan algebras case, which done before, you should reproduce again. All that things you should reprove for your algebras.
Yeah, this
is a simple part. Yeah, this is a simple part. But their problem is not producing algebras by using cocycles. The problem is after getting the algebras, then classify them. Are they isomorphic to each other? The resulting algebras are isomorphic to each other or not? That was more important problem in that previous classes of algebras. But you haven't reached that level yet. You're just giving some general theory for that.
Yes, that's true. Will be a further step, but as people, when they are working on this classification of the axial algebras, by now they want to know what types of, as this is so broad, let's say, they are not, let's say, so interested in getting the, or at least not so interested yet in getting the specific isomorphism class of algebras, but saying, okay, but what types can we have, right? Can we describe them maybe in a more theoretical way? Like, okay, all of these are going to be in correspondence with these other objects or these other algebras, or what types can we find? But maybe not to have a real list of, okay, this algebra is not is isomorphic to this other or not. And that kind of work has been done for example, for the axial algebras of monster type, which are generated just by two axes. There is a very nice work and very long work from a Japanese guy, I think it's Yabe, in which he solved the isomorphism problem, for example. But for this particular case of two generated axial algebras of monster type, whatever. But yes, it's more involved, and no, we haven't yet got there yet. Thanks.
Thank you. More questions? So these results were published already or only in preparation?
In preparation, we have been working on this for quite a long time, and I believe that now it's ready to submit to some journal, and we want to do it this week.
Okay.
And then we'll see if we are lucky or not.
Okay. So if there is no questions, let's thank Pilar for interesting talk and wish you success in this direction.
Thank you very much.
Okay. So, Jobber, is there any other talks next time? Jobber,
keyingi dokladimiz 17-kuni Tuyulbay Qurbonboyev, 24-kuni Braziliya universiteti professori Artur Lapatin.
Okay.
Keyin yana bitta zaifga tushyapti. Sobirjon Shaymardonov dissertatsiya ko'rinishida qilmoqchi ekan. Yana bugun zaifga tushdi.
Okay. Thank you. So,
Okay, thank you all.
see you in our seminars also. Bye-bye. Sabırıyla hammeyle hayır. Selamat boluyla keyin ko'rishguncha.
Xo'p, sog' bo'ling.
Mayli, sog' bo'ling.
See you again.
Rahmat. Sog' bo'linglar.